All right, recording is rolling. It is Tuesday, September 13th. So we're gonna score those projectile labs from yesterday. You guys just turned in your projectile quizzes. And then we're gonna get started on actually the next unit, which is which is dynamic, like forces. So we're getting there one step at a time. All right. Oh, let me show you some new pages that are on your desk. Right, so one thing you have are these new chapter 4 puzzles. Okay, right, and I went ahead and circled the numbers that we got to pick up from you guys. So that those are going to be due a few weeks from now. You guys have some time, right? So I have to teach this stuff to you first. I have to do a bunch of examples. So Friday 9:30, I'm going to pick these up, and then there's the next AP classroom open. That's unit 2. So have those done by the morning of Monday 9/26, and then we'll do like we did the other, we'll take a day and go over those solutions. Okay. As always, here, guys. As always, you guys know the solutions are provided. The solutions are provided here. Now, how are you going to do these? I mean, I have to teach you how to do these first. But once I teach you how to do these, are you going to think very hard on them and then struggle with them and then work with them and then check your answers with the solutions later? Or are you just going to turn your brain off and just copy the solutions, which is the right way to do that? Yeah, how about the first thing I said, right? Yeah, you need to struggle with them, think of them, right? This class takes some deep thinking. You have to make the neural connections, right? If you just turn off your brain and copy the solutions, you're not going to learn anything. Just cheat yourself, right? And then same thing with the progress check. Sure, the answers are out there on the internet. They're probably not hard to find, but like sit there and struggle with them and think about them. And if you miss them, it's not going to hurt your class grade, right? As long as you just do it, turn it, then you are good. Right. I also gave you guys a packet of conceptual questions, so like 60 conceptual questions. So we might hit some of those as we go along. I'm not going to pick that up, but that's just an extra resource for you guys. Okay. All right. Let's go over this this lab. You guys remember yesterday you were trying to figure out what's the launch speed of the projectile? We're talking about the launcher. What's the speed of the launcher? Right. Okay. Now there were different mass balls, so different groups are going to get different answers. There were also different setups you could do. So I threw 3 options on here to tell you guys what to, just so you have this extra information. All my other classes, besides you guys, I directed towards this particular setup where they were on top of a 4-meter tall ledge. They just launched horizontally and boom, just landed there. Right? You guys have left it more open-ended since you guys are AP. There's a little bit more creativity on your part, how exactly you want to approach this. But I'll show you guys what the answers would be, regardless of what your setup was. Right, and then I'll break out the. Do you guys have a crayon on your desk? A crayon, right? So I'll have you guys grade yourselves. Right, so one very simple setup would have been just to launch it straight upwards. Now, if you launched it straight upwards, you could have taken advantage of that third kinematic formula, this one right here, because you guys know at the maximum height, what's the speed? 0. So there would be enough information here you could have solved for the blast speed. Okay, and that would have looked exactly like this. And the square root, the answer b blast is square root 2gh, where h is the maximum height. You see that all over the place in physics. You've actually seen it before in this class already. Remember Galileo dropped stuff off the Leaning Tower? How fast was it crashing? Square root 2gh, where h is the height of the Leaning Tower. Okay, you're seeing it now. You're going to see it in the future. Yeah, it might be good to hold on to that in your mind, right? The next probably most straightforward one was the one I had all my other classes do, which was just launch it horizontal from the top of 4-meter tall drop off, right? Now, if you went with that setup, it would have been a 2-parter to get to the answer, right? What's the launch speed? First, you had to calculate the time of fall based on the height of fall. H equals 1/2 gt squared. That look familiar? Okay. And then you could rearrange that and solve for t to get the time of fall. Now, falling 4 meters, it takes almost a second. It's like 0.9 seconds. Right? But there's the general expression for it. Then, if you want the launch speed, that was also the horizontal component of velocity because you would have launched it horizontally. So it's just how far did it go? D, that's the horizontal displacement, divided by that time. And the time you got from up here. Okay, so looks like that. Consolidate some variable, and there you go. So if you know how far it went D, and what the drop height was H, this is the expression that will always get you the launch speed as long as you aim it horizontally. Okay, boom. That's it. Just little substitutions. Step 1, step 2, done. Okay. Right. Now, a lot of you guys I saw went with this type setup, which is a little more complicated. And then there was 1 or 2 ways that you guys went with this. Right. So if you just measured the angle theta with a protractor, or actually there was a built-in protractor, right? And you also measured how far to go this horizontal displacement d, called the range, right? then you could just use the range equation that I showed you guys a few days back, right? And just that you probably used on your quiz too, right? You just rearrange it and solve for V blast, do a little algebra switcher. Look at that, couple algebra steps, boom, answer, right? Now you can, whatever the distance was, whatever the angle was, whatever the gravity, whatever, you could even hot planets with this, couldn't you? Go to a different gravity field, right? And then I did see one team that did something kind of special. They actually measured the maximum height, right? Which actually, there was a homework question that was very similar to that. You guys remember the jumping puma? Right? It was basically that, right? So if you went with that, then you could use that third kinematic equation. Now, here's how I would have done this. I would say, well, if you look at strictly vertically, then whatever the blast speed was times sine of theta would have been the vertical direction, right? And the vertical, guys, what's the vertical velocity at the very top? 0, right? Now, of course, you're moving horizontally, but if you just focus vertically what's going on, then it would have been 0. So you got V sine theta going up at the bottom. That's like how fast it's going strictly upward. 0 at the top. You rearrange it, boom. V blast is that answer. Right, boom, 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 down. Look, it's just a few object steps, right? You guys see like the big picture of like how to do that, right? So this is all being recorded. So if you need to go back and take a slower or longer look at this on the video later, then there you go. That is it right there. All right, but let's break out a rubric so you guys can get a sense of how AP might score this. Now, there's a little plus or minus factor on exactly how you design a scoring rubric. So I might modify this a little bit as we go along here. Right? Guys ready? Right, now, there's actually 2 rubrics here. There's a completely different one for trying to figure out what's the optimal angle to launch the furthest distance. We didn't do that one. So we're going to focus on this on the left side. Okay. So you guys remember I told you this is 5 parts. 1, 2, 3, 4, and then conclusion would be step 5, right? So there's 5 parts right there. Yeah, conclusion, right? All right, so you had to have a question. What's the firing speed of the launcher? That's what had everybody stopping, right? Measuring tools. So 1 point for a meter stick. I mean, you had to have a meter stick somehow involved, right? If you listed a meter stick, give yourself a point, right? Okay, now here's where I'm going to modify this a little bit. On here, I put 1 point for a scale to measure the mouth of the ball. Change my mind on that. You know, if you reference a scale, go ahead and give yourself that point. If you use a protractor instead, because some of you guys use a protractor, go ahead and give yourself a point for the protractor instead. That would have been a more important measuring tool than the scale. And tell you what, if you did the whole thing with the meter stick, which technically would have been possible, then go ahead and just give yourself both points, right? Okay. Right, so you got up to 2 points so far. Right. All right. Data gathering procedure. Now remember what AP is looking for. They're how to measure what variables using what aforementioned tools. Right. Everybody was definitely using a meter stick, and then depending on what your setup was, maybe using a protractor, maybe using other things, right? Right. So now you would list this out like, you know, sentence by sentence. So the first sentence, something like this: set up a ball launcher. Here, you might have done at the top edge of a cliff, or you might have said put it on the ground. You might have said aim it horizontally, or you might have said aim it up at some specified angle, or you might have said aim it straight up, right? So there's a bunch of possibilities, right? And I just showed you guys here's different pictures that could refer to that. In fact, drawing a diagram could be a good idea, especially if you have time, right, and it matches up with the sentence. So give yourself a point for just having a brief description of the experimental setup. AP's going to be looking for something like that. It looks just like 1 sentence, right? Right. If you don't have something like that, then well, you know to write something like that in the future. Number 2, step 2. Use the scale to measure the mouth of the ball. Keep the mouth controlled throughout the experiment. Tell you what, if you mention, I'll make this really general. If you mention any kind of control, if you said use the same, if you just said use the same mass of the ball over and over, or if you said use the same angle over and over, or the same drop height, right? If you mention some kind of control, go ahead and give yourself a point for that. I'm modifying what's actually typed on the page here, right? If you mention any kind of control variable, right? Now, most labs in the future, there's going to be some kind of independent variable, and you could like possibly draw a graph. This was a simpler version. You don't even have to have independent variable with this one. You just do multiple trials with the same thing. Step 3, I've got measure the height of the cliff with the meter stick. If you had this setup, or a lot of you guys did this setup, in which case maybe measure the launch angle with a protractor, right? So give yourself a point for use of whatever measuring tool, either the meter stick or the protractor. Okay, but you had to mention at least one, or maybe both of those up here. So now say what data you got using that tool. Okay, you got a point. Step 4, launch the ball and spot where it lands. Right. Or some of you guys spotted its maximum height. So I got that in parentheses because you may have gone that direction. Measure that either horizontal or vertical displacement, depending on your setup, with the meter stick and record. Right. So 1 point for our use of the meter stick and this specific application. Okay. If you did the whole lab with just the meter stick, which is possible, then go ahead and do point, right? That's okay. And then step 5. Okay, now this is always a point. This is always a point they're looking for. Repeat step 4 5 times and find the average displacement, or if you did like 3 or whatever, right? So just 1 point for multiple trials, right? AP's always looking for you to say, I did multiple trials and like took an average, okay? Because there's always going to be a little bit of error and whatever exact trial. Okay, you guys get that? All right, let's keep going because these are this particular FRQ is always out of 12 points, so I tried to do something that added up to 12. Okay, all right, so that's the end of the data gathering procedure, right? You know, brief description setup. Then I use this tool to measure this thing, blah blah blah, all the way down. Right. All right. Now we're on to data analysis. Data analysis. Now analysis is where you either make graphs or equations. This one isn't really a graph type lab, but equations. You're definitely breaking out those equations on that green poster over there, right? Right, so I've got if you did this setup, if you did this setup, if you did the setup, right? So let me do it in the order that I explained it. If you launch the ball straight upward, you guys choose that third kinematic equation, BF squared equals V naught squared plus 2AX. Right. So 2 points for the correct kinematic equation, then substitute the average blast height into the equation to determine the blast speed. So 2 points for rearrangement to solve for V blast. Okay. That's if you launch it straight up. Okay. If you did this, like launched it horizontally from the edge of a cliff, then you'd want to use h equals 1/2 gt squared to and then rearrange it to solve for time times the square root of 2h on g, and then use that to determine the blast speed because that would have been horizontal velocity, right? X divided by t, but t was square root 2h on g. That's that exactly the expression I just showed you. Okay, remember this? I showed you guys right here. Boom, step 1, step 2. You guys remember that? Okay, that's just that. All right. So 2 points for correct kinematic equation, and then 2 points for rearrangement to solve for a V blast, right? On this page, it's all solved in terms of variables, so you could have gotten any height, any distance, any gravity field for that, right? Okay. And then I think a lot of you guys did some version of this here, right? Where you launched it at some angle, right? So it's like had it set up to look like this, right? If you did that, apply a kinematic formulas to derive a range of formula. Now that would have been a little bit more complicated, but I did that with you guys, so you would have had that in your notes. Right? Rearrange the range formula to find an expression for blast speed. Right, so it ends up being this. V is the square root of gx divided by sine of the double angle, right? Which is there it is. Square root of gx divided by sine of the double angle. Boom, just like that. Right. Now you guys, you can just look at your notes, say, okay, well, this is the range formula, and then just do a little algebra and just rearrange it from there. Okay. So 2 points for correct kinematic equation and 2 points for correct substitution of the values and then solving for V blast. Okay. Yeah.
If you use a stopwatch, that's time for you.
Yeah, do it. If you did that. So yeah, I was trying to cover as many situations as I could here, but if you have a stopwatch, then just make your best judgment as to like how that would fit in here, like what step that would replace. Like, okay, yeah, well, I would have gotten that point for that. Okay. Yeah, so I'll leave it up to you guys because yeah. Okay, and then last step, conclusion. Remember, the conclusion answers the question. Remember, the question was what's the blast speed? So the blast speed of the launcher is blank meters per second, and you guys have a unit on that, right? Maybe you did centimeters per second, but yeah, meters per second, right? What's the number you guys got for launch speed? What'd you get, like?
8.458 meters
Oh,
per second.
That's what all my students begin all day, about 8.5 meters per second. Yeah, no, plus or minus a few meters per second. So it's on its right a bit. Actually, that was like the most common number I heard over and over, about 8.5 meters per second. All right. Right, so you guys good there? Right. So use that crayon to score yourself out of 12. All right, and just hang tight for a couple minutes. I'll have you guys turn that into the gray tray, but not yet because I want to get you guys started on the next deal here. All right, so the rest of today, Do you guys see a lab page looks like this? All right, this is gonna be a team lab page. You guys can go ahead and put multiple names on this. You know, if you want your own or if you want an extra one, I do have some extra copies. Let me know. I can get you some extra ones too. You guys work at teams on this, right? And I'm gonna have you guys use the spring scale. Now we're going into Unit 2 by AP's book, which is called Dynamics, which involves forces, Newton's laws of motion, this sort of thing. So, guys, all the forces is just a push or a pull, right? And the way you can measure a push or a pull, this is a good tool for that, the spring scale, specifically pulls, right? If you're pulling like a tension, right? And guys, what's the unit for force? Newton, right? 1 Newton, by the way, breaks down to, here, I should write this down. 1 kilogram meter per second squared. 1 Newton is the same thing as 1 kilogram meter per second squared. Right? And I'll show you guys why that makes sense. And you might have known before you ever walked in this class, maybe from middle school or something. You guys remember Newton's second law of motion? F equals ma. Does that look familiar? Right? If you push it with a force in newtons, it will cause a mass measured in kilograms to accelerate its own meters per second squared. Right? Or here's, I actually prefer it this way. Acceleration is a net force acting on some total mass. Right? You guys see this and this is the same thing, right? Right. And then in terms of units, that's why 1 Newton is that. Right. Now, I do want to tell you guys a little bit about the spring scale so you know about the tools that you're working with. Right. If I pull with like twice the force, do you think this spring is going to stretch twice as much? And 3 times the force, it's going to stretch 3 times as much? Right. It will. That's a linear relationship between the force and the stretching distance. That's called Hooke's law. Right. Hooke's law. Okay. And Hooke's law goes like this. F equals kx. Some textbooks throw a negative sign there. I don't really care about that so much. Just think about direction, like which directions you're talking about. Okay. But this is like the pulling force. Right? Here's force. Okay. X is the how much the spring is stretched or compressed. No, with the spring scales, they can only be stretched, right? But other springs might be able to compress, and this works both ways. Okay. Here, if I draw a picture, let's say this is an unstretched spring going on right there, right? Okay. And if I put a force on both ends, okay, you can put like an equal and opposite force. That's called Newton's third law. You have to put force both ways, right? Some force here, some force here. Same force, okay. And see how this might have been stretched by this amount? I might call that X in this formula. That would be the amount that stretched, right? Or some textbooks do delta X, like a change in X, right? But I'm gonna just call it X. Okay. Okay. So what's K? Does anybody know or what that might refer to? It is the spring constant, which tells you how stiff the spring is. Yeah. That is called spring constant. Good call. Spring constant. I'll say stiffness. Okay, how stiff the spring is. Okay. Now you have different spring scales with different springs in them, and I'm about to go over that with you guys. Right before I do, I think what the units would be for these things. Like force, you guys told me is measured in newtons, right? Okay. X, you could do centimeters, more generally meters, some version of that, centimeters or meters. Okay. So you guys remember we did dimensional analysis, like unit analysis way back in the day, right? Here's where that thing come into play. I bet you guys can figure out what the unit is to measure how stiff a spring is. It'd be what per what? How about newtons per meter? Do you guys see that? If you have some number of newtons per meter, multiply by a stretch of meters, you get the number of newtons that you would need, right? You guys see that? Okay. Okay, so you could quantify here. There are these different spring scales scattered around the lab tables, right? The blue ones are hardly stiff at all, a little tiny force. It's like nothing. Right. The brown ones I usually give you guys, but like those are being borrowed right now. These are pretty versatile because they have kind of a medium stiffness. They go up to 10 newtons. Right. The blue ones only go up to like 2.5. Right. Ooh, so I bet the brown ones are like 4 times as stiff, right? Okay. Then next up are the red ones. Those are probably pretty as close as you're going to get to the brown ones. They go up to 20 newtons. Twice as stiff. Ooh, I feel some resistance there. Okay. And the stiffest ones out today go up to 30 newtons. Yeah, it's even stiffer than the other ones. Really stiff spring there. Okay. In fact, a good lab one day, we won't do this today, but maybe one day would be to actually calculate. I wonder what the spring constant is on each of these. Maybe if you guys want to do a little side quest today, we figure that out. Okay. You guys good so far? Okay, so you guys got the lab page. Now, this lab page is 10 mini labs. That's what it is. So, lab by lab, I'll give you some assignments. Say like, try this, try it. I want you guys to see and think to yourselves, how are forces being distributed? There's one that involves like changing angles. There's, yeah, you got the chain gang going on here. I wonder what the force is, as it distributes down the chain. Okay. Now, just to clear up a question I always get, number one, I want you to treat mass as an independent variable and write IV. So you'll choose different masses. Okay. Number two, use the same mass over and over. Same mass. Just distribute them a little bit differently, kind of like shifting. Like you can stand, you can like put more weight on one leg versus the other leg. This is kind of the tension version of that. Okay. But okay, number one, you're using different masses over and over. Okay. Number two, using the same mass over and over. Okay. And yeah, I think that'll get you guys going. Right. So there are 10 mini labs here. Yeah, work with each other and I will walk around and help you guys out. All right, and that is a wrap on this recording.